Hello everyone. Okay, so I know quite a few of you have been doing the play, and we just kind of need a review of what we've covered so far. And an important thing that I know a good chunk of us missed was these exceptions to the octet rule. So sometimes, right now, by the way, I'm on page 9. So follow along with me, check on page 9. If you don't have this filled out, fill it out with me. If you do, just follow along and have this good review before the quiz. The quiz will be on Tuesday, by the way. So we know from prior examples that we are trying to get to an octet, that we had, like our goal was reaching 8 valence electrons, except hydrogen and helium we're only wanting 2. Well, that's an example of this sub-octet. Like we saw that 8 is not always the goal. Like for hydrogen and helium, these guys were only wanting 2 valence electrons instead of 8 valence electrons. And it turns out there's a couple other atoms that when they're in the center, so first off, this is important, these other ones I'm going to mention, not the hydrogen and helium, but these other ones I'm going to mention, this only happens when they're in the center. And that would be boron, beryllium, or aluminum. These atoms will have sub-octets. They're capable, or they are very stable when they have less than 8 valence electrons. If I look at this example, and I'm going to redraw this with the bonds. Hydrogen. Right now, this boron feels like it only has 2, 4, 6, not 8. And that is more stable than having 8 when it comes to boron. Same with beryllium. If it has less than 8, it's more stable, and aluminum, that's true. I'm going to explain why with formal charge in just a moment. Okay, so sometimes we have less than 8. Sometimes we have more than 8, and that would be an expanded octet. So look at this phosphorus. This phosphorus right now feels like it has 2, because remember how each bond is 2 electrons, 1 from each atom, but both atoms feel like they have ownership over it. So like this hydrogen feels like it has 2, and this hydrogen feels like it has 2, even though they each only brought the 1 in. So this phosphorus feels like it has 2, 4, 6, 8, 10, so more than 8. Okay, again, this is okay, but only for the center. And we need atoms that are in periods 3 through 7, okay? And when I'm talking about a periodic table period, not groups, but 1, 2, 3, 4, 5, 6, 7. These are our periods. So they need to be in periods 3 through 7. Any of those ones are actually big enough to fit the extra atoms around them, and phosphorus is right there. So it's a large enough atom that it can fit the extra chlorines around it. An expanded octet does not happen on the outside. Like if we look at this chlorine right here, this one feels like it has 8 valence electrons, okay? Expanded does not happen on outside atoms, okay? Only on central atoms, okay? So the reason why this happens is something called formal charge, and formal charge will tell you it's your way of determining if there is a sub-octet or expanded octet, okay? And so it's your way of determining if there's a sub-octet or an expanded octet. So, reminder. How many valence electrons an atom has when it's neutral, and the amount that it brings to a molecule can be determined from the periodic table. So any of the atoms in group 1 have 1 valence electron. Group 2 has 2 valence electrons. We're going to skip 3 through 12 because it kind of varies through there. 3 valence electrons for 13. 4 valence, 5 valence, 6 valence, 7 valence, and then group 18 is 8 valence electrons. Okay. So here is an example of a suboctet. We had boron, and it was bonded to hydrogens. And we can see that boron only has 2, 4, 6. Well, I'm going to change this. What if we gave it a lone pair so that it was actually obeying the octet rule? Now, why is this not better than this one? And it has to do with formal charge. Okay, here's how formal charge works. The first thing that you do is you look at how many valence electrons that atom has when it's neutral. So the boron in the middle, oh, it's got 3 valence electrons. Okay? So this boron has 3 valence electrons. And right now in this molecule, it's assigned 1, 2, 3 valence electrons. When the amount of electrons it's assigned in a molecule is equal to the valence electrons in the periodic table when it's neutral, then its formal charge is 0. Let's do this for hydrogen as well. Hydrogen, when it's neutral, has 1 valence electron. And in this molecule, hydrogen has been assigned 1 valence electron. And so its formal charge is 0. Now, I'm not talking about how many it feels like it has, but how many are assigned to it. So this hydrogen is only assigned 1 of the valence electrons to it, and so all of these have formal charges of 0. Okay? That's optimal. Our goal is to find structures that have formal charges of 0 or as close to 0 as we can be. Those ones are more stable. Where if we look down at this one here, the hydrogens have formal charges of 0 still. 0, 0, 0. But boron doesn't anymore. So look at this. Boron is right here, and we said 3 valence electrons, but it is assigned way more than 3. Right now, this boron is assigned 1, 2, 3, 4, 5. Those ones up above, 4, 5. So it has 2 more valence electrons than what's on the center. So that means it has an extra 2 negative electrons. And so this would be a formal charge of -2. So when I'm comparing these structures, even though this one has an octet and that one has a sub-octet, less than 8, I would choose this one because all the formal charges are 0. Let me give you another example. Earlier we did a problem where it was sulfur dioxide, okay? And we came to this conclusion. We had sulfur, there was a lone pair on it, one side was a double bond, and one side was a single bond. Like this. And that gave us an octet for all of these atoms. But we also know nature tends towards symmetry. So it's like, we did a double bond here. What if we did an expanded octet on this sulfur? And we like take this lone pair and we move it over there. Sulfur, double bond, double bond. Same amount of electrons in both. I just took this lone pair and turned it into a double bond. Okay? Which one is more preferable? This one obeys the octet rule, 2, 4, 6, 8. This one has an expanded octet, 2, 4, 6, 8, 10. But it's okay because sulfur, okay, sulfur's right here, period 3. So sulfur can have an expanded octet. It doesn't have to, but it can. Well, let's check. When oxygen is neutral, it it has 6 valence electrons. Let's see how many valence electrons are assigned to it in this one. 1, 2, 3, 4, 5, 6. So that means it has a formal charge of 0. It's assigned the same amount of electrons as when it's neutral. Sulfur is in the same group, so it also is 6 valence electrons when it's neutral. This sulfur has been assigned 1, 2, 3, 4, 5. So it has one less negative electron than when it's neutral. So if it's one less of a negative, then that would give us a formal charge of +1. Now this oxygen, when it's neutral, it has 6 valence electrons. Let's see how many in this molecule. 1, 2, 3, 4, 5, 6, 7. So it has an extra electron. It's assigned one more than compared to its neutral form. So that would be a -1. Okay. Where this structure, remember oxygen when it's neutral has 6, so 1, 2, 3, 4, 5, 6. So formal charge of 0, formal charge of 0. Now let's check on the sulfur. When sulfur is neutral, it has 6. Right now in this molecule, it's been assigned 1, 2, 3, 4, 5, 6. So it also has a formal charge of 0. So even though this is an expanded octet, this is a better, more stable structure. Okay. The other thing that we did is we just practiced this. So we had a sulfur tetrafluoride, and we had a beryllium difluoride, like 2 fluorines here. Let me help you with this one. So step 1, whenever we draw a Lewis dot structure, is count those valence electrons. So sulfur, we know, has 6 valence electrons. Fluorines have 7 valence electrons, and there's 4 of those in there. Okay, so 28 plus 6 more, 34 valence electrons. Okay. Step 2 is we draw the skeleton structure. So I'm going to put sulfur in the middle and put my fluorines on the outside. Step 3 is doing lone pairs for the outside atoms first. So these fluorines each brought 7 valence electrons, but right now in the skeleton structure I've only drawn 1 of their 7, so I need to fill the rest of them in. So 1, 2, 3, 4, 5, 6, 7. And I would do that for the rest of them. Okay, great. Our 4th step is to now do valence electrons for the middle. So sulfur brought 6 valence electrons with it, but right now we've only are representing 4 of them. These 4, 1, 2, 3, 4. So there's still 5, 6. There's 2 more, and we would just put them as a pair on the center. I know that looks kind of funny, and I don't care where you put it around the center, but it is just a lone pair on the center. So this is an expanded octet. This sulfur feels like it has 2, 4, 6, 8, 10. And the formal charges will confirm this. So fluorines, when they're neutral, they have 7 valence electrons, and each of these fluorines have been assigned 2, 4, 6, 7. So they all have formal charges of 0. Sulfur, when it's neutral, has 6 valence electrons, and look at how many are assigned to it right now. 1, 2, 3, 4, 5, 6. So its formal charge is also 0. So that's a really stable structure. Okay, now if you haven't done this yet and you're following along, I want you to hit pause and draw this, and then afterwards hit play and see how it compares to mine. If you've drawn your structure like this, all of the formal charges will be 0. If you've made those double bonds to satisfy the octet, then we no longer have formal charges of 0. And so this is no longer a preferable structure. Okay, so everyone, same thing. I'm not going to show you yet, but hit pause and try this selenium hexafluoride. And just a heads up, selenium Se fluorine 6, okay? And then same thing here, xenon number 3, it's a xenon tetrafluoride. So that means 4 fluorines. So I want you to draw both of those and then do your formal charges to see if you've done it correctly. And then once you're done, hit play, and then I'll show you the answers that I got. Okay, so I'm going to reveal those answers in 3, 2, 1. Okay, so if this is your structure for selenium, then you have a formal charge of 0 on all of those. I know, doesn't that look crazy? There's so many atoms around there. Right here is our structure for this xenon tetrafluoride. So we definitely have an expanded octet with 2 lone pairs on the center, but all of those atoms have a formal charge of 0. Okay, same as before. I want you to draw the Lewis dot structures for A, B, and C, and then do the formal charges and make sure all the formal charges are 0. And then when you're ready, I want you to check your answers. So hit pause, give that a go. Okay, I'm going to reveal answers in 3, 2, 1. So here's what we would have for the chlorine with the trifluoride there. All of those have formal charges of 0. And then here's what it would be for B. And then here's our answer for C. And in all of these structures that I've just shown, they all have formal charges. Every single atom has a formal charge of 0. And so that just supports where we get these expanded and suboctets from. All of those, though, were expanded octets. Okay. So, what I want you guys to know is that we don't always do suboctets and expanded octets, but formal charges will tell us if that's the case. So even with this one right here, and we've obeyed the octet rule, we still get formal charges of 0. Hydrogens bring 1 valence electron, and they're 1 valence electron when they're neutral. So all of these have formal charges of 0. Nitrogen has 5 valence electrons when it's neutral, and in this molecule it's been assigned 1, 2, 3, 4, 5. So it has a formal charge of 0. So whether it's a normal octet, a suboctet, or an expanded octet, as long as our formal charges are 0 or as close as we can get to 0, then we've got the most ideal structure, the most stable structure. Okay. This worksheet is just practice on that. And so if you want to give this a go, and then I'll show you the answer key right now. So you have this. When it's, don't forget, when it's an ion, like a plus means that we lost a valence electron. So normally that would be 9 valence electrons, but it has a plus, so then it only has 8. And we put them in brackets with that positive charge. Where it was a minus, this normally was 7, 6 from oxygen, 1 from hydrogen, and then we gained 1 more to get 8. So whenever it's an ion, plus or minus anything, we put them in brackets and we put their charges on the outside. In class, we also talked about how carbons like to form chains, and they like to be in the center. So the center is actually a 2-carbon chain. And then same here, the center is a 2-carbon chain. And so we practiced that in class as well. but make sure that everything that has formal charges of 0, and make double or triple bonds if needed, and don't add any extra or use any less of your valence electrons. So like this is 10 valence electrons, and look, 2, 4, 6, 8, 10. And then if you calculate formal charges, every atom will have a formal charge of 0. Okay. And then here's this. Okay. And then last page, and if you don't have time for all of them, that's okay, but make sure you get enough practice in so that you know how to approach these Lewis dot structures. Okay. And then the last thing I want to talk to you guys about is starting to recognize when a molecule is polar. And this is really going to be based on if we have symmetry or asymmetry of these molecules. Like we learned from before that a bond can be polar or nonpolar, but really we need to see, first off, does it have polar bonds? And if it does have polar bonds, are those polar bonds symmetrical around a center or not? Because if it is symmetrical around a center, then they can all cancel out and the whole thing could be non-polar. One of the main contributors to asymmetry, though, is lone pairs on the center. So I'm going to tell you right now a little quick hint for you. If there is a single lone pair, that throws off the symmetry. So it doesn't matter what these bonds are, if they're polar or non-polar, this is a polar molecule. It has asymmetry. Same with this one. This is a polar molecule. There's more than one here, so this may or may not, and I'll give you more clarity on that next class. And so just distribution of electrons. Are those electrons kind of being evenly shared amongst everything, or do we have areas of the molecule that are more negative or more positive? And we will go over that in much better detail tomorrow, and then we're going to review on Friday. And then the last thing, so going over this tomorrow, reviewing Friday, and then on Tuesday we're taking our quiz. Okay? All right, everyone, thank you so much for your hard work, and I'll see you in class.